Okay. Okay. So we're discussing this week integration with you. It's mostly computational discussion. There will be some detours to theoretical questions, but mostly it's a computational discussion. Now, from the point of view of a concept, integration for functions of many variables, the construction of that integration goes in line with the one-dimensional integration. So this is a slide. This is a slide which makes this recollection from the first year. How do we construct? How we construct integration for the function of one variable? Everything spins around this integration sums or integral sums. So what you do, you partition your interval into the smaller subintervals with no restrictions. You can do it in any way you wish. For each of the smaller subintervals, you compute two numbers, the inf and the sup of a function, and that's symbolically on this slide. We use the notation f underlined and f overlined to indicate the sup and inf of a function across every interval, kth interval in particular. You multiply them by the length of the interval. You combine all of you collect all of this sum together. For the infs, it's a lower integral sum. For the sup, it's a upper integral sum. And here comes this tricky thing. You say the function is integrable when you can select a unique number I, which always squeezes between these two numbers. If you can do that, function is called integrable. If you can't, then function is not integrable. Of course, in practice, you don't really do this through the definition. There are a few criteria which you can use in order to ensure that such a number exists. For instance, when the function is continuous, which is very often the case, then function is integrable. There is such a result in the first year. So in practice, when you see a function and you intend to integrate that function, you don't have to check whether you don't have to compute the lower sum, the upper sum, and then try to analyze whether there is a unique number in between. Instead, you just say we have a result which says for continuous functions, it is integrable. This result, it's a deep result because bringing this together or connecting these two things, continuity and the existence of such a number in between the lower and the upper sum, it's a difficult task, difficult mathematical task. But it has nothing to do with the computations. In terms of the computations, function is continuous. We're good to go with the way we compute the integrals. Newton, Leibniz, or fundamental theorem of calculus, whatever. So we take this construction and we just develop this to the case of two variables. It's the next slide. That's what it does. This time you take two partitions. So in fact, we only consider rectangles on this slide. So first, that's how it is done. You take the rectangle on the plane. You partition the one side and the other side into the smaller subintervals. Two different partitions. They may be of different size. There's no any restrictions. There's no any relations between these two partitions. Any possible partition in the smaller subrectangles. For each of the subrectangle, you compute the inf and the sup. Again, symbolically, it's the same thing. F underline, it's the inf across the rectangle. F overline, it's the sup across the rectangle. You compute these two sums. You call them totally in line with the first year approach. You call them the lower integral sum, the upper integral sum, and you make the same definition. If you can find a number I in between, which is unique for every possible choice of a partition, there are plenty of choices for the partition, infinitely many choices. But if you can produce such a number, which works for any possible choice of partition, that's your integral. This is the sign that the function is integrable, right? Here it is. That's exactly here on the page number 5. If you can produce a number, unique number, which sits between these two, then function is integrable. Again, let me just emphasize this. Doing this directly, verifying this claim that there is such a number and such a number unique, it's a difficult verification, difficult logical verification. So we will need some criterion, like we had in the first year, which will take this burden off us. Like a function is continuous, it is integrable. We do have such a criterion. We will discuss this a bit later, but for now, that's the definition of Riemann integration. Well, that's a technical slide, basically. It just tells us that that's a thing which you have to keep in mind. With a double integration, And the argument behind this is the same as the argument for the single variable or functional one variable integration. You have these expectable properties like linearity when you integrate a function of, or when you integrate a linear combination of two functions. It's the same as if you take the linear combination of individual integrals. Monotonicity, it's when you replace a function with a larger function, point-wise larger function, right? So it's a point-wise relation between the functions. Then a similar relation between the integrals will stay. So the integral of the g will be larger than the integral of f. Number 3, it's basically a consequence of number 2, because f is always dominated by absolute value of f, point-wise. That's why you can use number 2 to conclude number 3. And the other one is the additivity. If you have two rectangles, if you unite them, then the integral across two rectangles will be sum of the individual integrals, sum of the integrals across two individual rectangles. Well, in case, of course, they have nothing in common. Yeah, in case, of course, they have nothing in common. Okay. Now, about the integrals, we need to know two things, basically, for the tutorials. The first two things we need to know is the geometrical interpretation of the integrals and computational approach. How do we compute the integrals? How do we find actually this I number, which delivers the value of the integral? The first one, to show you the geometrical interpretation, it's the next slide, it does so. It just says this. If you have now a function, f, if you just make this 3D picture, this is the underlying rectangle. This is a graph of your function in 3D. With the dots here, the picture shows you the partition of the underlying rectangle. So when you build your lower sum, it's a lower sum, right? The underline here, what you do, you're just stretching these vertical upright boxes, and you stretch them all the way until the minimum value of the function across the underlying little sub-rectangle. So every time, because the minimum value, every time your box will go just right under the graph of your function, you lift all of this, you lift all of these boxes for every of the underlying rectangle, you collect them together, and when you take all the volumes of each such boxes, right? Because this product, it's the area of the underlying sub-rectangle, this is the height of your box. So the triple product, like so, it delivers the volume of such box. You collect all of these volumes. This lower integral sum delivers the lower approximation to the volume under the graph of your function. That's the whole idea behind the lower sum. It delivers this lower approximation. Similar trick if you do the similar analysis of the upper sum. This time you stretch your boxes upwards, but this time you stretch them up to the height of the max of the function across the subrectangle. So this time the box will be always above, slightly above, or just sharply above the graph of the function. When you collect all of these boxes, the volumes of all of such boxes, the upper sum gives you the upper approximation to the volume under the graph of your function, volume of the solid under the graph of your function above the rectangle. And from this observation comes actually the exact interpretation of the integral of function of two variables. It delivers the volume under the graph exactly, in case, of course, function is integrable. And that's the thing which is used very often for like geometrical problems or problem from physics, this interpretation of the double integration. Yeah, that's what is said on this slide. For a function of one variable, Riemann integral is interpreted as the area, signed area, under the graph of the function. When they say signed, it means that when your box goes down, the volume is in fact negative. Or the area is in fact negative. For the function of two variables, the interpretation is the volume, but again it's the signed volume, which means that if your graph of your function goes under the level z equal 0, the volume is taken with the negative sign. Yeah. That's the interpretation of the Riemann integration. So it's one thing which we need to know. The function of for the function of two variables, double integral, it's effectively the volume under the graph of that function, plus or minus, depending where the graph is. The second thing, we need to know how to compute the double integrals, and that's what is done by the Fubini's theorem. That's right. So the Fubini's theorem says that in case you're looking at continuous function, look at this. In case you're looking at the continuous function over a rectangle, you can compute the double integral in the iterated process. Meaning that you compute the one variable integral, first year integral of your function by keeping one of the variable fixed, like in here, for instance, this inner integral, it's right here. You see, it just says when you interpret this symbol, integral from a to b, integral from c to g of fx, y, dx, dy, you interpret it like so. First, you compute this number in brackets. So you think of your function fxy as a function of y alone, and you keep your x fixed. As a function of y alone, it's a function of one variable, you can in principle compute the integral of that function because function is continuous, so it is integrable. When you finish this computation, you will end up with the value which will depend on x, right? If you change your x here, it will be another function of y, which you integrate, another value. So this bracket, this large bracket, it's sort of by itself, it's a function of x, right? Changing x changes the value of the integral. And then this function in bracket, this implicit function, which we don't have a name for, you integrate this new function with respect to the x between a and b. The number you will come up with, it will be the number for the double integral of f above the rectangle. That's the idea of the Fubini's theorem. Yeah. So once again, you basically just consider your function as a function of one variable, either x or y, by keeping the other one fixed. You integrate over this other variable. You will come up with a number, and that number will change depending on which value you fixed your first variable. So it will be another function, which you can integrate again. Yeah. And that will be the value of your integral. That's right. Any questions? Yes.
You said the function is integrable if it's for such a value I between the upside and lower side. And from the graphical interpretation, intuitively, it's like you must have such a value from the upper ring side and the lower ring side.
Mm-hmm.
Is that because of discontinuity or something like that you make a function not integrable?
Discontinuity by itself doesn't make a function non-integrable.
Yeah.
There are examples of discontinuous functions which are still integrable. There are plenty of such examples. Like when you have just only one discontinuity, the function will still be integrable. So no.
How could like such a function gets, you got such a how could like you got a value I not between the upside and lower side?
It is more often will happen that it won't be unique. Do you know the example of the Dirichlet function? It's a famous example of Dirichlet function, which is not integrable. Does anyone know a non-integrable function? Let's just start with this. Very simple question, isn't it? I guess many of you here think that they are really good with integration, isn't it? It's one-dimensional integration, right? If I confront you, are you good? You say, yes, I am, right? I passed the first year, right? 80% or whatever, you got it there, right? At least 75, otherwise you won't be here. So I guess each and every one of you think they are good with the integration, right? If I give you the integral from the first year book, you'll crack it in the 30 seconds. Now, here's a question to you. Do you know a function which is not integrable? Yes, we'll get back to that. Who said there are many of them? Can I see this person, please? Give me another example, except the one which you just named.
Well, like some complicated, just combinations of functions.
Well, combination of elementary functions is always continuous. Continuous function is always integrable.
Well, you can't calculate it.
Well, if you can't compute this analytically, it doesn't mean it's not integrable. It's still, there's a number which represents the integral. There's a number which represents the area under the graph, isn't it?
Yeah.
You may not be able to find this number sharply, but sorry, but it's your problem, right? It's not the problem with the function, it's the problem with your ability, isn't it? No, not your personal ability, I mean the person who cannot... You see what I mean? So I need the objective example of a function where there's no area under the graph. Not like someone cannot compute this area. So
Do we go on calling after a name, but it's like continuous everywhere? But
I didn't. So you have to say it again. I didn't catch that.
after a name on the equation, but it's like
Well, actually, the person renamed the function. It's when you take 0. Yes, please.
Is a function with an open end interval?
With the I'm not sure what you mean by with the open end.
Well, like if you put it on a
I mean when it grows to the infinity quick enough, like 1 on x to the power r.
yeah, yeah.
Like 1 on x.
All of a sudden we remember so many examples, right? That's right. Actually, it's another good example. If you take an elementary function which grows to the infinity over the interval, like a 1 on x to the power alpha, for instance.
An open interval like open A, open B. It's like it's a straight line that's open on each end. Can you like draw it?
Well, if it is bounded, it will still be integrable. You need to make sure it's unbounded. If you drop the endpoints from the interval, but the function stays bounded, it will be integrable. Yes, but if you make it go to infinity, sometimes you will end up with a non-integrable function. But it's a different integrability. Normally, classical construction of the Riemann integral goes for the interval with the closed ends. And my question was, do you know any function over the closed interval which is not integrable? When you drop the ends and when you push the function to the infinity, that's good, legitimate examples. But it's a slightly different integrability. It's like a wider interpretation of the integrability. So far, we heard only one example from the back there. If you take a function which is 0 at every rational point and 1 at every rational point, it's called Dirichlet function. It's a famous example. It's famous because it's not easy to come up with a function which is not integrable in a canonical classical sense. Just wait a little bit, it will come up. Yes, Dirichlet function. Yeah. Well, that's a general form of the Dirichlet function. It says one value for rational, the other value for irrational. Classically, normally people take 0 for irrational, 1 for rationals. It's a very easy function to think of in your head. It's hard to picture, of course, to make a picture of that function. If you try this criterion definition of the integrability on my first slide, just take an image of this function, 0 for irrationals, 1 for rationals. Let's just go back to the slide. Let's just scroll back to the definition of the... Here. If you compute the lower sum for such a function, what will be the lower sum? 0. Because infimum every time, because no matter how small you take the interval, there will be an irrational point in that interval. And the infimum will be 0. What will be the upper sum for this function? Well, it depends, of course, on the length of the interval, but when you take it over 0, 1 interval, the upper sum will be 1 again. Because no matter how small you take your partition, there will be a rational point inside. And the max of the function, or sup of your function, will be 1. Right? So the lower sum is 0, the upper sum is 1, and here's the contradiction. You can, of course, come up with a number in between, but you cannot come up with a unique number in between. There are plenty of numbers in between. That's a typical case for the non-integrability. It's not like the number falls outside the interval, lower, upper sum. The number will be between, but there will be plenty of those numbers. Okay? That's the typical case when the function is not integrable. Yes, please.
Could you write that function analytically?
Yes, actually, if you just check this page, they wrote it analytically. Here we go. That's an analytical formula for that. Any more questions? You don't like this, right? You want to like something a plus b equal 2, right, or something? Well, it's not an elementary function. We cannot express it as a cos, sines, or elementary combinations. You see there's some limits there, but still it's some sort of formula for this function. Any more questions, please? Okay, so you need to master the skill of taking double integral and repeating it. So taking double integral and converting it into the two one variable integrals, repeated one after the other. For the rectangles, it's a very easy thing. For the areas not rectangles, we're going to discuss this a bit later, it's a little bit harder, but still it's doable, and that's the first skill you have to manage in this in relation to double integrals. So for the rectangles, here's the example. That's right. So here's my function. Two variables, continuous, no problems with the integrability. Continuous function is integrable. Segment, a rectangle, 0, 3, 1, 2, right on this picture. Basically on the slide they do this computation. Look at this, what they do. They repeat the integral. When I say repeat, I mean they convert the double integral into the repeated ones. So it's the inner one, so you fix your function, you treat your function as a function of y, keeping x fixed. You integrate this blue one, that's the value for the integral, that's the antiderivative for x cubed, which is x4 and 4. Double substitution, 1, 2. If you finish this evaluation, that's the number you will come up with. Quite expectable, as we said, as we observed earlier. It's a number, it depends on this fixed variable x, right? It's 15x by 4. And now you integrate this once over against over x. That's the integration. Linear function, antiderivative x squared on 2. Double substitution 0, 1, that's the value for the integral. That's right. You have to make this clear distinction between the repeated integrals in your heads. Conceptually, it's two different things. Double integral, written like so. You see, integral over r of f. On these slides, they even skip the differential signs here. And the repeated one, like so, where differential signs are present and the order in which you write this differential is important. Well, you can make the same computation in the other order when you first treat y variable as a fixed one. I think it's the next slide, does the same computation, you see. The same function. This time we treat y as a fixed one. So we take x antiderivative, which is x squared on 2. Double substitution. Again, as expected, the inner expression, this blue one, because we kept y fixed, this expression end up being dependent on y, 9 on 2y cubed. Now we integrate this with respect to y, antiderivative for y cubed is y4 on 4, that's right. Double substitution, and here we go. Geometrically speaking, what happens is this: you fix your y variable, so you take your function only on this straight line, blue line, and you integrate across this line, and then you move this across the rectangle here in the second integration. That's right. Now, that's an interesting line, actually. Sometimes you will see it from, like probably in the way your tutors do the solutions. You can also argue a little bit differently, and that's the line which explains that. Look at this. Look what it says. It says, again, I do my Fubini's theorem. I replace my double integral with a repeated integral, or iterated integral. It's another name for the same thing. So the inner integration is the x integration, and the outer integration is the y integration. Now, when I look at this inner integration, because it's an x integration, this factor, y cubed, it's a constant factor. As we know for the one-dimensional integrals, the constants can be taken out. If you take this constant, that's what is done here. You see, the constant came out. Now, when you look at this integral next to this constant, I mean x dx from 0 to 3, there's no any y there anymore. It's just the integral of x alone and the function of x alone. So this whole thing, this whole integral as a whole is just a number which can be factored out of this y integration here in front. That's what is done here. And effectively your double integral, after these few steps, your double integral just came out to be just product of two individual one-dimensional integrations. It's a very typical case which happens when you integrate over a rectangle and when your function, that's another thing which is important, when your function is factorizable in a pure x and pure y factor. If this is not so, if your function is sort of some very complex combination of x and y, where you cannot split them in two factors, pure x and pure y factors, this line is not going to work. But when you can, and in this case we can, you see it's a pure x factor and pure y factor, y cubed. When you can factorize the function in pure x and pure y factor, and you integrate over a rectangle, you can always expect this. When your double integral becomes just a product of two individual one-dimensional integrals. After a while, actually, what I do often with the people who are experienced with the double integrals, I just jump straight from here to here, when I see that the function is factorizable and you integrate over a rectangle. Okay, any questions? Well, the page number 13, it's a lengthy explanation. Basically, the purpose of this explanation to give you the idea how the Fubini theorem is proved. On the conceptual side, I think probably most of you, after a while, you will realize what you need to do to prove the Fubini's theorem, and that's basically explained by this display line. When you take this integral sums, lower sum or upper sum doesn't matter. In this case, they took the lower sum. You see this underline. When you take this lower sum, and that's how it looks, you can do this repeated procedure. You can just single out from this double summation across j and k. You can single out only j summation, and then you just make the k summation later afterwards. When you do it, then you can claim that inside the bracket you have sort of like the integral sum for the one-dimensional integration, and this will be the integral sum for the other one-dimensional integration. That's how the Fubini theorem is proved, actually. But there is a problem in this approach, which must be addressed. The problem is that when you take these inf values, they're not happening on the same line. That's what explained in these two paragraphs. Well, that's what the Jonathan Kress tried to explain in these two paragraphs. So when you look at this bracket, and when you try to convince everyone that this bracket is in fact the lower integral sum for the one-dimensional integral, where you fix which variable you fix here, because k is go for the y, so basically y is fixed here. So when you try to convince everyone this is the integral sum, there is a problem, because these values where inf is happening, in case you look at the continuous function, for instance, the values where inf is happening, they are not sitting on a straight line, and that's why this sum is in fact not the integral sum as you hope it could be. Well, the two paragraphs below, they try to explain what you need to do in order to make it the integral sum. You need to use the continuity sum epsilon delta argument. We're not going to do this. If you like challenges, you can try to do this. And these two paragraphs, they will give you the guidelines how you can finish that. But that's all I plan to tell you about this slide. Yeah, and the purpose of this slide, once again, just to give you the idea how the Fubini is actually proved and what are the pitfalls you will meet if you try to do that. Yeah, well, actually, it doesn't. It even gives you another approach in the book. Actually, it's an internet supplement to the book, page 6570. Well, if you like challenges, you can try and read that or try to read that. Any questions? Another result in relation to the integration, it's about what happens if you have non-continuous function. You will have some non-continuous functions. They will be mildly non-continuous, so they won't be as bad as the Dirichlet function, for instance, which has, how many discontinuities the Dirichlet function has? The function we just discussed, the one which has zeros at irrational points and ones at the rational points. How many discontinuity points that function has? Infinitely many, you say? Can you be more specific, like name them all? all of them. That's right. Actually, that function, this is a function which is discontinuous at every point, every one. Yeah. And that may be the reason why it is not integrable, actually. So, on the other hand, your example, like examples you're going to look at, they will be mildly, if they will be discontinuous, they will be mildly discontinuous. When I say mildly, it will be not many of the discontinuity points in those functions. And in, on that case, they will be integrable. All of those functions, in fact, which have discontinuities but still integrable, they are summarized in this result. Let's just read that. It says this: if the function is bounded over a rectangle, and if it has the discontinuity points, but all of them sitting on on finite union of graphs of continuous functions, then f is integrable. So you may think of this as this: you have this rectangle, you can run through this rectangle some sort of curves. Graph of a continuous function is a curve, isn't it? If you can run through this rectangle some curves, how many you like, doesn't matter, as long as you have finitely many of them, you see? Finite, it's an important piece here. You can run these graphs of any function through your rectangle. If your function f, original function f, is discontinuous on these points, sitting on these graphs, alone, and over the rest of the rectangle it is continuous, you find function is integrable. You can cut your rectangle by like a straight line cuts, and you can assume that the function is discontinuous across the straight line cuts. As long as you make finitely many cuts, the remaining function, or the function like so, will be integrable. That's the purpose of this result. The purpose of this result, to extend our view a little bit wider beyond the continuous functions. Because continuous class for the integrability, it's a very restrictive class. There are lots of good examples you need to know, but which are not continuous. So remember this: even if the function is discontinuous at some points, as long as you can put all of these discontinuities on some curves through the rectangle, as long as you can do that, the function will stay integrable. Yeah. Again, we're going to skip over the proof of such a result. It's not an easy proof. And in fact, it is not a standard way how people normally do this, but for our purposes, I think it's a good way to state this. Yes. Any questions? And that's the version of the Fubini's theorem. Fubini's theorem is the one which converts double integrals into the repeated integrals, into one-dimensional integrals, in case your function is not continuous. So before, there was a claim that the Fubini theorem was given for continuous functions. This time, we're going to give them for the functions as in the which are suitable for the previous theorem. Look what it says. Basically, the formula is the same, but here you have to be a little bit more careful, because I think it's explained here in the last sentence. If you're dealing with not continuous function, it's the one which may have discontinuities on graphs or on some curves, continuous curves running through your rectangle. It may happen that when you consider this one-dimensional integral, when you fix one of the variables, but the other one is the one you're integrating over, it may happen that this integral is no longer makes sense, because one of the curves where a function is discontinuous may be this vertical line, right? And the vertical line when we keep, for instance, x is fixed. And in that case, the integral of this type is no longer making any sense. So when you apply your Fubinis to the function which is not entirely continuous, which has some discontinuities, you have to make sure first, you see, that's the piece in this theorem, you have to make sure first that this inner integral, when you fix one of the variables and you integrate over the other variable, this inner integral always makes sense. If you can make sure of that, then you can proceed with the Fubini's computation. Yeah. That's the thing, that's the extra loading you have to take care of when you do the Fubini for discontinuous functions. In practice, it doesn't really look difficult, but still you have to keep in mind that you have to do this thing. Right. Now time has come to discuss with you what happens when you integrate functions not over rectangles but some other domains, some other areas. Again, it's not only, here comes not so easy subjects. In fact, you can't do it over any domain you wish, like it or not. You can come up with the really freaky shape domains on the plane over which you cannot integrate even super continuous functions. So when it comes to integration of function of two variables, it's not only the goodness of the function which is important, it's also the goodness of the underlying area which is equally important. Okay? When it is rectangle is a perfect shape. We have no problems with rectangles. But when you move on to the other shapes, here the quality of that shape becomes equally important as the quality of the function. So in our, actually it's not in our case, most of the time when we integrate over the domains different from rectangles, we must see that these domains fall into these two categories which are on this slide. We have actually, this slide introduced a name for these domains. We call them elementary regions or elementary domains, and we subclassify them in two subclasses, Y-simple region and X-simple region. And that's the diagrams which explain what we mean by that. Y-simple region, it's the one which is bounded by two graphs of functions of X. So you see on the sides, they're bounded by two vertical lines. On the top and the bottom, they're bounded by two graphs, like this. In that case, we're going to call it Y-simple region. X-simple region, it's the one which is just where the X and Y rows are swapped. This time, from the top and from the bottom, we control the domain by two horizontal lines. On the sides, we control them by two graphs. This time, these are the graphs where X and Y, you see, they swap their rows. X is, the left-hand side here is a function X equal psi1 of Y. The right-hand side here, it's another function, psi2. That's the geometrical look of these two domains. That's the formal writing, which represents these two domains. You see, collection of all points, all pairs, x, y, where x is bounded by a and b on the left and the right, two vertical lines, and y is bounded from above by one graph, from below by the other graph. The G1 type, or Y-simple regions. This is the X-simple regions, analytical form, or analytical writing for the Y-simple region. For these two types of regions, we can develop integration as well. We can develop the Fubini way of computing the integral. I'm sorry. There is a distinction between these two things. Yeah, there is a distinction. So, I mean, there are domains which do not fall in either of these categories. Can you come up with such a domain? I'm thinking as much as you are. Well, if you take, for instance, the annular region, circle with the missing with the partly missing interior, that's the one which doesn't fall in either of these categories. Okay, so for that domain, you won't be able to apply Fubini way of computing the integrals, even though domain itself, circle with the partly missing interior, it's a good domain. The double integral will exist for that domain if you take a good function. So you see that there are some distinctions here. I said it before, for the integral to exist, not only you need to have a good function, you need to have a good domain, but for the integral to be computable for the repeated Fubini process, the domain must be even more, from the even smaller class from one of these. For the other classes, Fubini process no longer works. And that's the only way you have to compute the double integrals. Fubini process, when you take the double one and you convert this into the repeated one. So for these two, Fubini works, and that's how it works. Look at this. That's what you do to link previous Fubini for rectangles to this new Fubini for the domains either Y-simple or X-simple domains. Look what you do. You imagine you have a D, which is the elementary region, either Y-simple or X-simple. What you do is this. You take the rectangle which is around this domain, which contains this domain inside of it. You introduce a new function. f star here. That's what you do to this function. You take this, you assume that your f star is the same as f within the domain and 0 outside the domain. So you have your domain shaped either y simple or x simple. You submerge this domain into the larger rectangle. Over the domain you had a function, and outside the domain but within the rectangle you take the 0 value to make your function existing across the whole rectangle. And then you say, if you want to compute the integral of the function over this particular domain, what you do, you take the integral over the rectangle, which we know how to compute, of this new function f star over the rectangle. And that's actually, at this stage, I think you will realize why we need this result about the integrability of discontinuous functions. If your function f originally was continuous, when you make this extension with 0 outside the domain, the function is no longer continuous. Every time you cross the domain, the function drops to 0 or jumps to 0, depending positive or negative value function had, right? So every time you cross, you go across the boundary curve of your domain, function just has a discontinuity. But how many of those discontinuities you have? They fall exactly into this category. They all sit on the graph of a function, isn't it? Look back. Look at this. If you go across this boundary, function has a discontinuity. But all of the discontinuities, they are on the graph of finite union of functions. So such a function, f star, it will fall into the category where the integrability theorem is applicable, the one we saw a bit earlier. That was the purpose of that theorem, to include all of this f star function into the realm of the integrable functions. So that's what you do again. If you want to compute the integral of a function over some fancy shaped domain, you submerge this domain into the rectangle, you make this 0 extension. It's a discontinuous extension, but it's fine in terms of the integration, because integration is fine when you have discontinuities only sitting on some curve or some bunch of curves, as long as your bunch is finite. And you take the integral of this extension as the integral of your original function. Yeah, that's what's said in this paragraph. F is continuous except perhaps on the points made on the graph. And now look what sort of Fubini shape, what sort of shape Fubini takes when you apply this Fubini for the rectangle. It's here. Well, it's done for the y simple domain here. When you compute the f, integral of f across y simple domain, you replace this domain with the enveloping rectangle R and the f star function. For the enveloping rectangle, you can do the Fubini. That's the Fubini done for the enveloping rectangle. Now, when you look at this inner integral between c and d of the f star, remember the y simple region is the one which is bounded by the function at the top and the function at the bottom. So when you look at this inner integral, which is across y, so the one which goes vertically, as soon as your integration goes above the function at the top, the function drops to 0, right? It's just said here. As soon as your y are larger than the function bounding your domain at the top, f star takes 0 value. As soon as your y value less than the function bounding your domain at the bottom, f star takes the 0 value. That's why this inner integral for the f star, which come up from the Fubini over the rectangles, it becomes the integral of your f function, no longer between c and d, but between the lower bounding function and the upper bounding function. And when you collect everything together, that's how the Fubini will look for the y simple domain. The integral, so for the y simple domain, you have no choice anymore, x or y. You can always go y first. You will always go y first, I'm sorry. For the y simple domain, y will be the inner integration, and the integration this time will go from the lower bounding function to the upper bounding function. That's the only way you can do Fubini for the y simple domain. By analogy, for the x simple domain, there is only one way to do Fubini, unlike rectangles where you had a choice, x or y first. For the x simple rectangles, you will go x first all the time. And this time you will go for the from the left bounding function, psi1, to the right bounding function, psi2. If you have any other domain which doesn't fall into the category y simple or x simple, you can't do Fubini. There are still some tricks how we can split the domain into the combination of y simple and x simple. And that's a trick which most of the time will work for you. But you keep this in mind. There are plenty of the domains which are very good, but sometimes they're not splittable into. Actually, maybe it's a false claim, actually. Maybe every good, let's just take it like that. I said that for the integration in two variables, you need both good function and good domain. Now, I can more or less give you a firm interpretation of the good domain. Good domain will be the one which can be split into the combination of either x simple or y simple. Because in that case, you can do Fubini. For parts which are x simple, you will do Fubini with the x first integration. For the y simple, you will do the Fubini with the y first integration. Yeah. Any questions?
And for the y simple and the x simple, for some domain, are they interchangeable?
You're saying that what you're trying to say, I'm guessing, is that there are some domains which can be classified both y simple and x simple. For instance, circle, right? Sorry, not circle, disk, interior of a circle. That's the one which can be classified both y simple and x simple, right? Or if you want to do it y simple, you will bound your domain with the upper semicircle from the top and lower semicircle from the bottom. If you want to do it x simple, it will be left semicircle from the left, right semicircle from the right. Yes, there are domains which can be both classified into the x simple and y simple. In that case, you can do Fubini both ways. That's right. But there are some domains which cannot be classified one way or the other. And there are some domains which cannot be classified either way, like disk with a missing interior, some part of the interior. That's the one which is not classifiable in any other way. But if you do some cuts through this disk, if you do some cuts through this annular region, parts of it can be classified as the either x simple or y simple. Any more questions? Well, it's the first thing we need to master, and probably the main thing you need to master, applying Fubini for domains different from rectangle, but either y simple or x simple. That's the skill we're going to discuss next time with you. Thank you very much. I'll see you all Wednesday.